Okay, so I have this satellite launcher that I put together. It's three stages. Stage 0 here is the actual satellite itself. It's got just under a kilometer a second of delta V. Stage 2 is this big, um, I guess, 4-ton liquid stage. It's got about 4,300 meters per second of delta V. And stage 2 is just this one single booster. This is just to get us through the bulk of the atmosphere, and this rocket is heavy enough that this one booster isn't going to get us above terminal velocity. So, saying we've got a total of 5,775 meters per second of delta V in a vacuum. It'll be a little less than that because a chunk of our flight's in atmosphere. What we're going to do is keep an eye on terminal velocity here and our actual speed here. Whatever your design and however you fly it, you want to make sure you keep your surface speed under the terminal velocity. This rocket seems to run full throttle without exceeding terminal velocity, but a lot of the times you'll want to make sure you're using liquid stages and keep the throttle turned down so you don't go too fast. I've had a lot of problems with using too many of these solid boosters because they'll go as fast as they go and you can't control them, and you just are throwing away delta V, which means you're throwing away fuel and the fuel you needed to carry that fuel. So we're going to do a standard launch here. We're going to go straight up to about 10 kilometers, push over to the east, climb out in a parabolic arc towards the eastern horizon. That's the most efficient path to orbit. We're going to shoot for a 100-kilometer circular orbit. So let's see how it goes. Throttling up to full. Stability on. And launch. You see we're 60 meters per second, terminal velocity is over 100, so far so good. It looks like this thing's leaning over to the east a little bit. Normally I'd like to keep it straight up. The little bitty reaction wheel I'm using for the satellite is the only control we have right now until the thrust vectoring engine comes on. We're at 100 meters per second, terminal velocity is 115, and we're leaning over to the east way prematurely. Alright, there's our second stage. Now we've got thrust vectoring, so we can fix our course a little bit. Again, 130 versus 150, so we're looking really good on speed. And you can see here that our drag losses are like half of our gravity losses, and that's what you want. If you launch one of these things and you see drag losses far exceeding gravity losses, that means you're exceeding terminal velocity and you're throwing away fuel. .90, 208. Alright, start easing over to the east, just using a little bit of yaw. And what we're looking for here is this 90-degree heading, and this circle here is the 45-degree inclination. So we're gradually pushing over towards 45 degrees of inclination on the 90-degree heading. And if you do this really nice and smoothly, you keep your steering losses minimized. And now what we're going to do is watch our apoapsis. We're going to watch the time to apoapse, and we're going to try and keep this somewhere between 45 seconds and a minute. And we're basically chasing the apoapse up. We're looking for 100 kilometers, and when we hit 100 kilometers, we're going to kill our engines. But if we keep this time right, and we do that by adjusting our inclination, then we can minimize our periapsis burn. And also you see that we're basically following the velocity vector. We're just kind of very gradually dragging it down towards the horizon. And the closer we are oriented towards our velocity vector, the less loss there is in steering, because the less we're trying to act in a direction other than the direction we're traveling. Now, it typically takes a minimum of about 4,500 meters per second of delta V to get into orbit. And you can see here we've used 3,500 already. We've got 1,200 remaining in our current stage. 80,000 meters apoapsis. We're looking for 100 kilometers. There's 92, 93, 98, 100. Alright, overshot just a little bit, but 105. Not bad for no autopilot. Alright, without these engines burning, we don't have a lot of reaction torque. We just got this tiny little reaction wheel that's part of the satellite. So when the engines are burning, you've got a pretty fair amount of thrust vectoring. But without that, it's very hard to control. So now we're looking for apoapsis. When we get there, get close to it, actually let's do this with a node, it'll be a little more obvious. So we go to the map view, we can add a maneuver node here, and then basically we're going to burn along our velocity vector, and that's going to increase our periapsis and circularize our orbit. So we drag that up until you see the nodes swap places. And now we've got 105 peri, 130. Let's circularize that a little more. So I'm going to shrink it, just kind of play with it a bit until this is pretty close to circular, and that looks good. Show the nav ball down here. So this is going to take 560 meters per second of delta V to accomplish this maneuver. And we have 839 in this stage, so we're fine. So we've got 2 minutes and 14 seconds to the burn. I'm going to go ahead and start trying to orient this thing. It's very difficult to maneuver, but what we're trying to do is orient towards this blue marker, and that marker indicates the attitude of the maneuver node that we set up. The maneuver that we set up. So assuming that we put our attitude indicator right on that blue target, and we burn when they say that to burn, and we burn the amount that it says to burn, then we will change our velocity vector by the amount that the maneuver node has set up, and basically we will change our orbit to this orange dotted line. So now we're pretty well lined up. We've got 1:25 to go. It says it's a 12-second burn, so I'm going to try and burn 6 seconds before and 6 seconds after. So I'm going to speed up time until we get a little closer. And back down to one speed. So we've got 13, 10, 11, 10, 9. At 6, I'll start burning. 7, 6. Full burn until this drops all the way to 0. Alright, now kill this node. Now you can see our new orbit is pretty good. got our orbital information here. Apoap's 105, periap's 98. Relatively low eccentricity, so it's a pretty good circular 100-kilometer orbit. Again, an autopilot could do it better, but I am flying this by hand. So we've still got a pretty fair amount of fuel left in our ascent stage, 283 meters per second, but I think I'm going to go ahead and jettison it. And really, that's all I had planned for this thing. I don't really have the fuel to take it anywhere. I put some goo pods on there, but I don't get much for them at this point. So it was mostly just some extra weight to haul into space for no reason. So I think I'm just going to let this thing orbit for a while until I can come up with something better to use it for, but I just wanted to make this video to make it a little more obvious how to get into orbit, how to use maneuver nodes, and all this information is mechanical jab, which is handy. I spent a lot of time doing this stuff on paper before I installed mechanical jab, and it certainly can be done by hand, but the game without the add-on doesn't give you a lot of information to do your job. You have to kind of, I mean, to the point of adding up the weights inside the assembly building. You have to add it all up on paper and do the math. And I made a spreadsheet. And this spreadsheet allowed me to kind of add up all the parts in each of my stages and then calculate my delta V's. But that's kind of a hassle, and having mechanical jab to do some of this for me is much, much nicer.